Hello, everyone. Hi, I'm Nikhil, and I'm my friend Madhu here. And we are going to talk about cluster federation in Kubernetes, and specifically how to write a federated controller. But before we get started, can we get a show of hands of how many people have actually used cluster federation? All right, a few. So just to make sure everyone understands what cluster federation is, so cluster federation makes it easy to manage multiple clusters. And why would you need multiple clusters? There can be many reasons, like you want clusters closer to where your customers are. You have customers in Europe, and you have customers in US. So you would want clusters in both those continents. You don't want cross-Atlantic latency. Or you want high availability, like you will have clusters in multiple availability zones. So even if one goes down, the other still continues to work. Or you might need multiple clusters for scalability. Or you want to avoid vendor lock-in, like you have a hybrid setup. You have one on AWS, one on GCP, or on-prem. So those are some of the reasons why you might need multiple clusters. And what federation specifically helps with is, like in this example, you can see you might have red, blue, and green, 3 different clusters. And you want to deploy your app across all the 3 clusters. So without federation, how would you do it? Your developer would have to create the same deployment across all those 3 clusters, ensure whenever you're doing a rolling update, you'll have to update all 3 of them. With federation, you get a single endpoint, which ensures that your app is in sync across all the 3 clusters. So instead of sending those commands to all those 3 individual clusters, you just tell federation that I want this app deployed, and this is the version I want, and federation ensures that it's deployed to all the clusters. You can do rolling update, rollbacks, everything works, and all the clusters are in sync. And once you have these apps deployed, you also want to create these network resources like service or ingress. Like if you have an ingress object, you want to configure that ingress in such a way that its backends are configured from all the clusters. Like if there are pods running in red, blue, green, all the 3 clusters, all of them should be configured as correct backends for ingress or your global service as well. So if you are creating service or ingress via federation, federation does it for you. It will automatically create the load balancer or the DNS rules for the service in such a way that all of those would be valid backends. And now, since your developer or your admins are talking to this single federation control plane instead of talking to each of those individual clusters, this becomes the single place where you can apply all your policies, like scheduling policies or auth policies, everything. You apply those policies in federation. And federation gives you a single point where you do that. So if you want to do it, how it really works, you first have to set up a federation control plane, and then you can join all the clusters that you want to federation. Once you've done that, you can use federation as in you'll use Kubernetes. Federation is 100% API compatible with Kubernetes. If you have your existing replica set definition, and you run like kubectl create replica set, and you send that request to kube API server, the same request can be sent to federation API server, and the defaults are configured in such a way that it will all work out. Like it, by default, balance the replicas across all the 3 clusters. And obviously, there are some additional advantages that federation gives, and you can enhance the replica set spec that you already had to take advantage of those federation-specific features as well. But your existing replica set spec that used to work with Kubernetes will work with federation as well. So like your your developers don't need to know that are they talking to a Kubernetes API server or a federation API server. They just get an endpoint, and the same Kubernetes resources work for federation. So to go deeper into the architecture, this is like a 30,000-foot view of how a cluster federation setup looks like. You see there are users on the right, and there's federation control plane, which is talking to your multiple clusters. The users can talk. There are various ways they can talk to the federation control plane. They can use the REST API. They can use kubectl command line interface or the UI. And you'll see those are similar to how you would talk to a Kubernetes control plane as well. And you send your request to federation control plane, which then sends it to the other clusters that you registered with federation. And for those of you who are familiar with Kubernetes, this looks very similar to how Kubernetes works. There are users who talk to Kubernetes control plane, who then sends those requests to nodes. So your developers don't need to talk to the nodes directly. They just talk to the Kubernetes control plane. And to go deeper into the control plane, in Kubernetes, the control plane consists of, these are the main components in the control plane. There's API server, there's etcd, and there's controller. So when users send their request to the control plane, they're actually talking to the API server, Kube API server, which stores the desired state which it received from the user and just stores it in etcd. And then controllers make those desired state happen. So what controllers do is they'll read the desired state that the user wanted from API server. Then they'll read what is the existing state of the cluster. And then they'll take actions to bring the current state of the system to the desired state. So if the user said, I want a replica set with 5 replicas, the replica set controller will observe that this is the user's intent. And right now in the cluster, I see only, there's no replica existing. So then it will go ahead and create those 5 replicas. So controller is the one that does all that work. In Federation, again, the control plane looks very similar. There's Federation API server, and users are talking to Federation API server. They express their desired state, what they want. It's stored in etcd. And then there's Federation controllers, which make that desired state happen. Now, to tell us more about how those controllers work, I'll invite Madhu.
Thanks, Nikhil. So before actually looking at how to write a federation controller or a federated controller, let's try to understand why one would want to write a federated controller or any controller. But before that, let's also do a show of hands again. How many of you attended one of the controllers talk either yesterday or today? We have talked, there were a number of talks about this. Okay, not many of you, I guess. Anyway, so what's the motivation? One of the main, the key powers of Kubernetes actually lies in its extensibility. It's a very extensible system. One way to look at Kubernetes is Kubernetes is an API server, so it ships a bunch of interfaces. And in the official release or the distribution, along with those interfaces, we ship a bunch of implementations. Those are the controllers. And there are other components like kubeproxy, DNS, and all those things, which could be considered as controllers because they do similar things. But these implementations cover most cases, 90 to 95% of use cases, but there are always cases which are not covered by these implementations. So in order to extend this implementation or extend the functionality provided by the default implementations or the default controllers, you might want to either augment or extend the existing controllers. One of the examples that I can think of is, let's say you have a replica set in, API object and we ship a replica set controller. But what if you also wanted to create an audit trail or audit log for every replica set created in your system, which is not provided by Kubernetes today. There are talks about providing it in the future releases, but it's not there today, and you want it now. So you could write your own controller to extend this functionality, create audit logs, like who created the log, at what time, who created a replica set, at what time was it created, and you could store in your database. You could do that today if you want to. Another reason why you might want to write your own controller is to customize the behavior. There are a number of implementations, examples for this today. The Ingress API object is the best example. Kubernetes for GCP ships an Ingress implementation, but there is an Nginx implementation. People have written their own implementation for F5 or any other load balancer that they have on-prem. So these are the key motivations. One of the other motivations, but far lesser motivation, is you might want to implement your own API object. Kubernetes, core Kubernetes as a cluster has this concept called TPR, third-party resource. We don't have that in Federation right now, but we'll probably have it sometime in the near future. But yeah, that's also another use case where you might want to have your own object and write a controller for it. With that, let's look at the architecture of the Federation controller specifically. For this talk, we have created a demo. I don't know how much the demo is going to work, but for this demo, we have created an API object called the foo object. It's called type foo. It's exposed via the Federation API server, and for that, we are going to write a controller today. So like a Kubernetes controller, if you're familiar with the Kubernetes controller architecture, the Federation controller is a binary. It's an executable that can run as a pod inside your cluster. So we have this controller called the foo controller. And just like the Kubernetes controller, it talks to the API server, but the difference in this case is it talks to the Federation API server, which is on the right here. What does it do? What do controllers do in Kubernetes? They watch for the desired state and reconcile. So in this case, this is the foo controller, and because we want to reconcile the state for the foo object, this watches for the foo API resource in the Federation API server. But in addition to that, this is special to Federation. Every federated controller also watches an API resource called clusters. This API resource lists all the clusters that are part of the federation. This is the key difference. Kubernetes controllers watch for the desired state in a Kubernetes cluster and reconciles the state in the same cluster, whereas federated controllers watch for the desired state on the Federation API server, but reconcile the state in the Kubernetes, underlying Kubernetes clusters, which are part of the federation. So we don't have clusters right now, but after you start watching the clusters, you probably also want to start watching the same API resource foo in all the underlying clusters. So if a new cluster joins Federation, you immediately want to start watching for the foo API type in the underlying cluster. So if another cluster joins, you want to start doing the same thing, and the same thing every time a new cluster joins. And you might also want to do some cleanup operations if you want when a cluster leaves Federation. So with that, let's go a little deeper. This is like lowering the conceptual levels. We looked at the conceptual architecture. Now let's look at the actual API types. And after this, let's go a little deeper into the code itself. So the Federation API server exposes the cluster's API type, and it also exposes the foo resource type. And we want to watch these API objects. These are the specific resource version and kind name. Federation /v1 beta1 /cluster is actually a real API resource type in Federation, and you can watch for this. And foo is another type that we added just for this demo. Then you watch for the same foo resource type, which is also exposed for this demo in all the underlying Kubernetes clusters. Once you do that, you basically set up your control loops, which reconcile. All you do, in this particular example, the only thing that we do is copy the object from the Federation API server to the Kubernetes API server. It does not really do anything interesting, but it demonstrates the idea of federation. So you basically watch for the desired state in Federation API server and update the state in the underlying clusters. And in addition to that, one more thing that a federation or a federated controller handles is cascading deletion. When you want when the object is deleted from federated API server, you want the same object to be deleted from all the underlying Kubernetes clusters. So with that, let's actually go right into the code. This is a little too much, I think, but let's see how much we can do here. So we talked about all these conceptual things. The first thing that we talked about was watching the foo resource. The controller architecture or the controller infrastructure in Kubernetes is actually a library that you can use. There's a lot of code in here, but I'll point out the important bits. Some of this is boilerplate, which is setting up the library or calling the right functions or the packages, methods. So we have a library called as the Informer library for writing controllers. Informer library is used everywhere in Kubernetes controllers. Every Kubernetes controller talks to API server or sets up a watch using the Informer library. So setting up the Informer library looks like a lot of code, but it's mostly boilerplate. It's not a lot, actually. And it can be easily copy-pasted, and that's how most of us start writing new controllers. We copy-paste from somewhere else and then start changing and then actually implement the logic. So this is how you set up an Informer. This Informer is basically setting up a watch for your resource type, foo resource type, in the Federation API server. So it says foo resource, And you need to provide two Lambda functions, which are implementations, which are basically to list and watch. Watch does a watch for the events in the API server. And we also need a list implementation because a watch uses a cache, and caches can go out of sync. So time to time, we do a complete resync, like list all the resources from the underlying API server and update the cache. So you need to provide these two implementations, list and watch, pretty simple. They just call the client functions, the appropriate client functions. And then you need to say what object you're watching, and then a bunch of other boilerplate. Once you do that, the second important thing that you need to do is watch the clusters. And the third important thing is to watch all the resources in the underlying clusters. These two are taken care by a single library. The other library is called as the Federated Informer library. Don't worry too much if you can't see it, see it in the back. Like you can go and look at one of the controller files. But the concepts are important. So this setup looks very much similar to the previous setup. It's just that here you're watching for the objects in all the underlying clusters, every cluster that is part of Federation. And in the bottom here, you also say you're watching the clusters themselves, the clusters object that I talked about. So in the implementations that you provide, you say what you want to do when a cluster joins or leaves a federation. So here in this specific implementation, we only say we care about cluster available. That is, we want to do something when a cluster becomes available or join federation. We don't really define what we want to do when a cluster leaves federation, but in a real controller, you probably also say cluster unavailable and supply an implementation for it. So these are the key things to set up the watches. And once you set up these watches, the other thing that you need to set up is the cascading deletion itself. Again, this is another library function where you call the appropriate function new deletion helper. You call the new deletion helper to set up the deletion helper, and you provide a bunch of implementations. All these are basically Lambda functions, or the functions themselves. So you provide these functions as implementations. We use the finalizer API to set up cascading deletion. The details are not that important. It can be, like you can look at the code, one of the controller's code, and just use the same code. We are also working on simplifying all these libraries so that you don't have to repeat the same things over and over again for controllers. But this is the current API or the libraries available. Once you have all these, you basically hook things up. You say you want to start the informer for the API objects, and then you say you also want to start the federated informer, and you start all of them. But one key thing that you do here is when you start the informers, you also register handlers. You want to say, you also want to define, or you define how you want the reconcile operations to handle. So you provide implementations for the reconcilers. There are two reconcilers. One is reconciler that runs whenever the cluster membership in federation changes, which is called reconcile foo's on cluster change. And there is another reconciler which runs every time an object itself changes. So you provide the implementation for these two types of reconcilers. And the implementation for the reconcilers are really simple. This is the reconcile foo's on cluster change. So whenever a new cluster, we only define what to do when a cluster becomes available. So this handler only takes care of cluster becoming available case. So in this case, if you look at the last few lines of code, which is important, first one is just the error handling part. This is the important part. Here, whenever a new cluster becomes available, what you do is you take all the objects you have in federation and copy it to the new cluster. So you basically do a list and copy. That's it. Deliver does the copy to the underlying clusters. And then the more interesting part, the real logic is implemented in reconcile foo function. All the federated controller logics are implemented, logic is implemented in this function, every single controller, but each controller has its own implementation. So here, every time the federation API object itself changes, you compare what changed, and if anything has changed, you propagate the same changes to the underlying clusters. And you usually don't want to do the operations every single time something has changed. So there is a facility or library to batch these operations. So you batch these operations and give it to the updater, which does the batch update on all the underlying clusters. So with that, let's try a demo.
Yeah, that was a lot of code, and we assumed all of you are software developers and wanted to see code. But we also have a demo, and hope it works. So what I have is, I have a federation control plane setup. I have two clusters on GCE, one is on different zones on GCE. One is in US Central 1A and 1F. And I've set up that this expose foo. Both those clusters and Federation API server also exposes foo. And what I'm going to do is I'll create foo, and I'll create it only in Federation control plane. And we'll see how the controller works and propagates it to the underlying clusters as well. Yeah, let's see if I'm able to connect to my machine.
Looks like the odds are not in our favor. Every single Federation demo since Tuesday evening worked. So law of averages has to work, Murphy's law has to work, and we are the unlucky ones.
Yeah.
And this is even basic SSH. What's that?
Yeah, you guys have already seen the code.
Yeah, let's actually move forward. And if it actually works, we can
come back.
Yeah, come back.
Yeah. All right. So yeah, so we've talked about a lot of stuff here, and all of that is not implemented. We have a lot of stuff working, like we have federated ingress, replica set, namespace, secrets, config maps. We have added alpha support for deployments. And we recently launched a new command line tool called kubefed, which makes it easy to set up the federation control plane, register clusters. And in 1.6, it's going beta as well. But there's still a lot of work left to be done. Like the ingress especially works only on GCP right now. It doesn't support hybrid scenarios. We want to do that. The federated services, you need a public endpoint for them to work, like the DNS rules that we configure. It uses Google Cloud DNS Provider or Route 53 if you're on AWS. But we want to make it work with private services as well. And we are improving how the access management and identity work. And the work that I talked about, that federation control plane becomes the single place where you apply all the policies. We are doing a lot of work there as well. So there's still a lot of work left to be done. And Madhu and I have been just lucky enough to be presenting it here, but we are not the only ones working on it. Like everything in Kubernetes, this is a community effort. We have a SIG Federation mailing list, which you guys can join, or we meet every other week, and we are active on Slack channel as well. And here you can see our email IDs and GitHub IDs, and you can ping us directly. If you're interested in any of the work that we listed, you want to contribute, we'd love to have those contributions. Yeah, and that's it.
SSH thing came back.
Let's see if that works.
OK.
Can you guys see this?
I think not. Can everyone see this? OK.
Yeah, so here I have the federation control plane set up, and I have two clusters. I set them up last night, and I have foo resource set up as well. So I can run kubectl get foos with federation, and I can do the same thing with the underlying clusters as well. So you can see here kubectl, I'm using the same kubectl binary to be able to talk to Federation API server or the underlying clusters as well. The way it works is I have set up multiple contexts, and I have a federation context, which is talking to Federation API server. And similarly, I have two other contexts, which are talking to those two underlying clusters that are registered with Federation. So now what I'm going to do is I'll create a very simple foo object. And I've created it in Federation, like kubectl context Federation. And this is how my foo looks like. It's a very simple object which says kubecon rocks. And so now what's happening in the background is the stuff that Madhu talked about. There's this reconciliation loop running in the controller. I have a foo controller running, which what it does is it observes that the desired state from the user is that this foo object should exist everywhere in my cluster. And what the current state of my cluster is that it doesn't exist in any of those underlying clusters. So what the controller will do, it will send create requests to both these underlying clusters. And now if I do the same kubectl get foos in the underlying clusters, I'll see this kubeconf foo object there as well. So it exists in Federation, and it exists in the underlying clusters as well. So foo controller did this fanning out of the request to underlying clusters, but it wasn't just at creation time. It's always running, always active. So what if I go ahead and delete this foo object from one of the underlying clusters? So I'll delete it from 1A. So since this foo controller is always running, it will again figure out that the desired state is that this kubeconf foo object should exist in all the clusters. But it got deleted from one, so it doesn't exist there. And it will again send a create request to that cluster, and again make sure that kubeconf foo exists in both the clusters. So if I run get foos again, I'll see it was recreated 13 seconds ago. And if you really want to delete this kubeconf foo object, you'll delete it from Federation API server, because that becomes the place of the source of truth. So if I go ahead and delete kubeconf foo from Federation, again the foo controller will observe that now kubeconf foo is not part of the desired state, but it still exists in the underlying clusters. So then it will go ahead and delete it from the underlying clusters as well. That shows it's always active, always running, always ensuring the desired state matches the current state. So now if I do get foos in the underlying cluster, it should say no resource found in both those clusters. Yeah, that's all I have. Glad that the demo worked. Yeah, that's it.